You almost came here at 11?
Yeah, because my brain got confused. So I was gonna come early, and that was one reason why I was in there.
Because your brain was confused?
No. Don't you ever get that?
I'll have a case of that for the rest of the day, yeah.
Really?
Study.
Oh.
Exams. When I don't say cram, but what do you call it when you're just like trying to memorize stuff?
Cram.
I mean, cramming indicates it's last minute, like. But
Did you study it last night to hurry up and remember?
I had already previously remembered. I just get stuff mixed up.
I still think that's called cramming.
Okay. Because cramming is a bad thing,
Yeah,
but
because you forget everything.
What are you trying to remember?
It's stuff or
stuff for biochem.
Oh.
I'm done remembering it though. I'm doing exam today, so now I can purge. This weekend I'll purge and start over next week, huh? Which I bet they have big jobs with this smart water.
no, only $2.
$2.09.
Only $2. You really commit to make an output.
Make an outcry on CMD. Why? What do you do?
Are you asking him or you suggesting him?
No, I want to see the structure that you gave me yesterday.
Okay, I can show it immediately.
No, I copied the entire directory. I just don't know how to read it.
Yes, I can show like visually.
Oh.
YouTube,
Oh, it's on.
Levi Lustrom.
Really? Oh.
No? No, I'm not sure if it is there.
Old Spice. How come that's the first result for YouTube Levi Livestream?
I don't
It's
know.
for deodorant.
Oh, it's that?
Yes.
Oh, that is very, very small. No,
Yes.
non-added battery coupling only took like 20 minutes.
You're done with the couplings?
For 60 of them,
Mm-hmm.
for 60 states or 60 time steps.
Uh-huh. Actually, I was planning to suggest this subject for Aaron to do, but he already is doing something more advanced and probably he doesn't have time to do this, but you can talk and cooperate and maybe compare several.
Yeah,
Stop.
Svetlana was like, you and Aaron should do a group meeting where you talk about your method. Like Aaron talks about your guys' method, I talk about our method. And then I was like, I don't know if I want to do that.
Well, so, are we expecting someone else to come?
What's the date today? 2/9.
See, they do have new screens, which are not
bigger.
a little bigger, not like drastically, but
What do they do with the old ones?
pardon?
What happened to the old ones?
Burnt out. Oh, Hi, Diane. Thanks for coming. Okay, so although we decided to start earlier, we're still under time pressure. We cannot spend too much time. We're gonna jump over.
No, there's usually space here. Stairs.
So you have enthusiastically decided to make presentations on coming Tuesday, right? I will announce the subjects in a few minutes. So in addition, if you feel very bored on the weekend, you can entertain yourself with the homework, which will be numerically find at which ratio of perturbation to diagonal energy the first order perturbation theory gives less than 1% error. So it is just trying the code that we were doing in the lab last night with different values of the perturbation. And I think some of you already have a hint of the value. What is it? Like 0.29?
0.28.2 using math.
So when we meet in 5 days on Tuesday, presentations will be related to application perturbation theory. We are finishing the second chapter, where we very briefly come through approximate time-independent approximate method, time-independent perturbation theory. In comparison to standard narration of quantum coordinates, we will not likely not consider variational theory because it was part of computational chemistry. And upon we finish the chapter crowned by your presentations, we will start time-dependent perturbation theory, which is even more important, especially in application of interaction between light and matter, but not only this one. So here is the list of your choices. So there were more than one choices for each of you selected first and second. So Diane agreed to present on Muller-Placid perturbation theory. Levi wanted to cover octahedral splitting in details. We will rearrange the order. The next one will be Sam, talking about scanning tunnel microscopy, and then Jabet will tell about perturbation in magnetic field, and Aaron will tell about spin orbit splitting related to fine splitting in hydrogen atom. And Brendan was very enthusiastic to take the hardest subject of van der Waals interaction.
What?
No, if you do derivations or if you just steal them and present them, it is the hardest.
Okay. How long you can understand down?
We will try to make same format, like 4 minutes per presenter. And although we have this plan, we will never follow it. It will be a little longer. We just need to make sure that those of us who need to be elsewhere at 1 p.m. finish before that. Okay, what are we going to do today? And who we are, where we are, what are we doing? So we are trying to find a bypass, a way to solve Schrödinger equation for systems for which this equation is insolvable. The goal is to solve insolvable. And the plan is to split the Hamiltonian onto part that has solution, either analytical or numerical, and then the rest is considered as small perturbation, we introduced the general philosophy of expanding both energies and wave functions in series of in Taylor series compared to this small parameter, and then we were successful in getting first order correction to the energy and to wave function. So there are two things that we need to cover before we will be done with this time-independent perturbation theory. It will be the second order correction to the energy and the degenerate case. At least if we are limited in time, at least the philosophy of the degenerate case, because in many applications, perturbation theory is exactly applied when the quantum states are degenerate, and perturbation lifts this degeneracy, like introduces splitting of d levels in transition metal complex, or splits the terms due to spin-orbit coupling or due to magnetic field. So where we did finish yesterday, not yesterday, on Tuesday, on this equation where the wave function can be approximately seen as zeroth order solution plus first order correction, which is expanded in basis of zeroth order solution, where the expansion coefficients contain matrix elements of the perturbation Hamiltonian in denominator and energy difference in denominator. And it is important that summation doesn't touch the orbitals that we are correcting, right? So what we will be doing right now, we are going to look at the term for second order correction in energy, and we will be plugging in this expression into there. So it is major part to keep this expansion coefficients, and then what we are doing will be completed really quick. Let me do a little experiment. Okay, maybe this time we will be able to avoid the board and do everything here. Good. So the here is the plan. There will be several steps. On the square term, then there will be an equation. These two terms on the left, three on the right. Then, due to Hermitian property, we will simplify it with one term on the left, two on the right, and then we will use specific orthogonality for different orders of permanent corrections. And after that, we will get very simple expression to which we are going to plug in the first order correction. And then we will get second order correction in perturbation theory. So our goal is second order correction. So, a brief review, which probably, should I call someone to the board? I'll do it myself, because it's very simple. I'll call someone when it will be really hard. So, Hamiltonian is zeroth order plus perturbation. Energy is zeroth order plus first order plus second order perturbation, and wave function as well. Zeroth order, first order, second order. We remember that in zeroth order the solution is known exactly. Also, when we did the first steps in perturbation theory, we were plugging in all three expressions into Schrödinger equation that should correspond to realistic exact situation. And then we were setting up that coefficients in front of the equal order powers should be equal, right? So in zeroth order it is this expression. For first order we were combining H1 psi 0, H0 psi 1, so that summation of the orders will be the same. For the second order, we need to, well, we can look back what we did about 10 days ago, or we can just use the symmetry. So we need combinations of perturbation, Hamiltonian, wave function, and energy with indices, so that the summation of indices will be equal to. So zeroth order Hamiltonian acts on second order correction to wave function. Plus first order correction to Hamiltonian acts on the first order correction to wave function. And then there is no second order correction to Hamiltonian. Therefore, operators are done here at the left part. Now for the energies. Energy zeroth order, wave function second order. Energy first order, wave function first order. Energy second order, wave function zeroth order. So if you look here, 0 plus 2, 2, 1 plus 1, 2, 2 plus 0, 2.
Why not H2 psi naught?
Huh?
I mean in left side. Why not H2 psi naught?
Because there is no H2. Because there is only first order perturbation.
No, we are considering second order here, right?
But we didn't
If you
define
look
H2.
how we originally derived, we will get, if you scroll back, we will get this one. Let's make a bet and scroll back. If you have doubts.
Yeah, I did the first one, but I didn't try the second one.
But it is what you get in the second one.
Okay.
Now, what is our philosophy for getting an expression for energy? Right now, we have operators and we do have wave functions, which are like matrices and vectors. And we need only number, only the energy. If I wanted to help. What are we doing?
conjugate again.
Yes, yes. So we are multiplying the complete expression by bra vector from the left. So in order to avoid wave functions. This is invisible. So we are taking zeros order, right? And construct this convolution. Zeros order, second order. Zeros order. First. Second, zero, first, zeros, second, zeros. And now all this brackets and index, which will be the same everywhere. So we have two terms on the left, three on the right. So it is 2 equals 3 step in our plan. So we need this one, we need this one. It's too long, we want to simplify. So here the Hamiltonian operator acts on the bra to the left and generates the energy. What do we get? Then the first term becomes E zero squared overlap convolution of the zeros in second order. And we should consider our efforts as a delicate and precious resource and avoid practicing calligraphy. Just let's look other similar terms anywhere in the left or right.
The first one.
Right? You see? So the first, we converted first term from matrix element of Hamiltonian to just convolution of Brian cat with energy in front. And here it is the same. Energies can be always placed outside of the convolution because it is a number and it doesn't change wave functions. Make sense? Okay. Then we do have first order correction. First perturbation. So now we have one term on the left and two on the right. So it is 1 equals 2 step in our plan. Can we simplify it further? Why? First, we derived it at the very first meeting about perturbation theory. Because the exact wave function is like orthogonal to itself, and there is no terms. And to double check that it is zero, we can take exact solution for first order correction, which is expansion coefficients in the basis of zeroth order wave functions. And if we overlap it with wave function number n, this will be zero because of orthogonality. So it is non-zero only if n equals k, but we set up explicitly n is not equal to k. So it will be, all of these overlaps will be zero. For sure, we can remove this term. And now we have used orthogonality, and we came to the equation one term on the left, one on the right. Can you say something about this term? Where we have zeroth order cat and zeroth order bra, and the index is the same. Huh?
1.
Yes. So we keep only E2 sub n. It is not the final answer, but it reminds us something, right? When we were considering first order correction to the energy. Let me write it down here. First order correction was matrix element of the perturbation in the basis of zeroth order wave functions. Diagonal. Right? You know, there are kids entertaining books without letters, only with figures in task. Find 10 differences in two figures. So find 2 differences in these 2 equations.
Cat. The order perturbation in the cat. Or
So first, you're correct. First, they have different indices for the answer, for the label here, and second, there are different orders of perturbation for the wave function in the cat. Right? So in order to get final answer, you need to plug in the expression for first order correction to wave function. Good? Brandon,
Oh no.
you'll be our hero today.
Just he already has the expression.
Oh.
Just don't.
Wait, what am I writing?
You are writing E superscript 2 in brackets subscript n
Okay.
equals
And then.
so now repeat this, and then make a little break.
Okay.
Now, look at the board there and just copy this stuff.
All of that?
Yes, all of that.
Okay.
I apologize that we need to practice too much of calligraphy, but it is needed. So we are plugging in the first order correction to the wave function. Not the whole approximate wave function, but only the first order correction. So in the nominator, it is matrix element of perturbation between Bra and Ket of the zeroth order wave functions with different indices, L and N, and in the
These are different, that's L.
yes, yes.
Oh,
Zeroth order. Good. And here we see there is a wave function, unperturbed wave function. And since we are using Bra and Ket, let's do this angular. Yes. Thank you so much.
Yes.
Aaron, would you please continue the chain of hero effects? Let's discuss what can we do. If you know what to do, just announce. If you don't, we'll discuss together.
I'm just thinking, well, this is like an expansion coefficient, right? So can we just pull this out to the front, or is it not constant?
Well, we cannot pull it out of the summation.
Right, we would pull a summation with it, but like pull,
Yes.
you pull all that out?
Yep. Everyone agrees? Please do. So Aaron put forward everything that is related to first order correction to wave function, except the basis vector of the zeroth order correction. Yeah, thank you. He's almost done, and now I take the simplest step. So this basis remained at the last, and this curved bracket traveled to the first. this part travel to there, right? So this is a number, and this is again a matrix element. Here probably I'm missing zeros. Matrix element of the perturbation to Hamiltonian in basis of unperturbed wave functions, right? And here we also have perturbation matrix element in basis of wave functions. Now let's look on indices. L, N, L, N. So if this thing is, if everything is good mathematically, like Hermitian, then swapping the order of indices shouldn't be changing anything. So we can just take absolute value squared. Summation L is not equal to N. L, perturbation N, absolute value squared, difference in energies. What did we get? Second order correction to the energy, right? So if we are able to split our Hamiltonian on something that is solvable plus small perturbation, and we want to solve and find energies, then first we should try first order correction, and if it is 0, which is typical in many symmetric situations, then we should go for the second order correction. And some people are not happy with this and going for third and fourth, but it is not practical for the learning process. In many cases, first and second order corrections are sufficient. Good. Let's take a screenshot for the future meetings and then cover one more little section. So, a little summary. We are able to solve unsolvable, right?
You know what you should suggest to them? Get a smart board.
Yes,
That would be
I do
great.
think that we will be able to learn how to write here.
They have a pencil, don't they, up there?
Maybe. And then save it in the
Yeah.
and then save these images so that we can distribute it among group members, class members. Next. So one of the examples you have selected for applications, for presentations, is octahedral splitting of energies of d orbitals in metal organic complexes, where these d orbitals have the same energy. And before, we had two subtitles to the stuff that we are discussing. First, we were discussing time independent perturbation theory, and second, non-degenerate. So in our denominator, we always had the energy difference. And if you will consider a situation when energies are the same, then the zero denominator will get to singularity, to infinity, which is not acceptable. It's not pleasant mathematically and is not helpful physically and chemically. I did why? Not in everything, in a little stuff. And it was just in pedagogical purposes to make narration quicker. So I was claiming that perturbation theory replaces exact solution of Schrödinger equation and replaces diagonalization of matrices. Yes and no. It is yes for non-degenerate, but it is wrong for degenerate case. The only good news or comforting side that we will not diagonalize the whole Hamiltonian. We will diagonalize only fragment of Hamiltonian that is related to the segment to those degenerate levels, degenerate orbitals. But for degenerate case, perturbation theory, one needs to diagonalize matrix. 5D orbitals is too complicated. Let's leave it to some of you to present. Let's consider something simpler. Just two degenerate orbitals. States. Definition. What does it mean degenerate? Meaning we do have two wave functions. Let's say A and B. If we plug them into Schrödinger equation, we get their eigenvalues, and degeneracy means that energies are the same. But at the same time, the wave functions are orthogonal. Typically, we have that if wave function coincides with itself, it is the same function, it has fixed energy, and then like if the indices are the same, then here is one. But here, wave functions have same energies, but they are orthogonal. And we do want to apply perturbation theory to such situation. If we combine some linear combination of these two degenerate functions, will it satisfy Schrödinger equation or not?
Yeah.
What will be the eigenvalue?
Some of these E and E.
Or let's think once again.
Oh, C alpha E plus C beta EV.
So you're telling that it will be eigenstate of the Hamiltonian, but what will be the energy?
Energy of alpha plus energy of beta.
Let's
Energies will be same as this one. Yeah.
yes. How do you prove? Well, let's just make an experiment in our head. If C alpha and C beta are equal, 1 over square root of 2. So it's equal probability for state alpha and same probability, 50% state beta. And then we find expectation value of energy.
We need to normalize.
But the energy for them is the same. So you can say that it is equal to energy alpha or equal to energy beta, right? So it will be the same energy. You can just select one of those. Why do we need this relation? Because we are going to play the same game and expand wave function and energy correction in power series for perturbation theory, and then we will multiply it by bra from the left and see what happens. And when we multiply by bra from the left, we will need to convert from operators and wave functions to numbers. And then we will use this property. This is the hardest part of our meetings. Okay. We do experiment. Here is the same place. What do? We do want only energies and only first order. So perturbation, first order energy plus zeroth order Hamiltonian, first order energy right? And we are considering that our Hamiltonian is summation of unperturbed plus perturbation. So, what are we placing in there as wave functions? Let's place their linear combination of these degenerate values and just inspect what happens. So linear combination of zeroth order Hamiltonian, and the linear combination first order. Zeroth order energy linear combination first order. Plus first order correction to energy that we are hunting right now times linear combination of zeroth order. So, just for curiosity, let's try to, well, we stopped being thinkers. Now we are algebraic machines that follow the prescription. We are doing the same thing for the last 2 weeks. Expanding in series, multiplying by bra from the left, avoiding wave functions, getting corrections for energies. Right? So we can teach a robot to do the same. What will we practice? What is this? What is this one? It's a food.
That's not it.
It comes from this.
Waft.
So let's try to multiply from left only by psi alpha. Only one of those degenerate values. Only one of degenerate states. I'm debating how far should we go in calligraphy, or we can think on the fly. Let's go first. We are going to do it twice. First, we will multiply it by alpha. Second time, we will multiply it by beta. First time, we will do calligraphy. Second time, we will try to be short. So, plugging in on the left side and opening all brackets. Psi, zeroth order, alpha, perturbation, coefficients in front, psi, zeroth order, alpha, plus coefficient, psi, zeroth order, alpha, perturbation, zeroth order, beta. On the left? No, not on the left, it's
Let's check
it's
it
just first term. Should we do it next time? No. We'll do it. Plus C sub alpha, the unperturbed alpha on the left, zeroth order Hamiltonian, first order for alpha, plus C sub beta, zeroth order alpha on the left, unperturbed Hamiltonian, perturbed beta. This was only left part. Now it's time for the right part. E sub 0 out of brackets, C sub alpha out of brackets, wave function zeroth order alpha overlaps with wave function first order alpha, plus energy zeroth order coefficient psi C sub beta out of brackets, wave function zeros order alpha, wave function zeros order beta. Two terms more. Energy, first order correction out of brackets, C sub alpha out of brackets, wave function zeros order alpha overlaps zeros order alpha plus energy first order out of brackets, C sub beta, wave function zeros order alpha overlaps zeros order beta. Whew. So it is time to simplify, to get rid of something. What?
The last term is 0. Oh, okay. So shocking.
Why?
Right there.
Because these degenerate states are orthogonal. Good? This is okay.
Oh, wait.
Here
Oh, this
again.
is
One. Yes, thanks for correction.
right.
Okay, keep it if you're not sure. Let's look.
But
What
then
else can
here we can get the energies,
Mm-hmm.
right? So then that's the alpha,
Yep, because they are equal.
and then that would be right.
Okay.
So
Yes.
that's
Mm-hmm.
that term.
Yep.
Then this would be similar.
Good.
Then you can't do that trick here, right?
No, you should keep them as
So
they
I
are.
think that's all I know.
Yep. Thank you. That's great. So this eliminated. This is one. What can we say about these terms? Just by analogy to what we did before. I have a big temptation to assume that they're zero. Because the orthogonality will be between zeros order perturbation in lambda term. And when we have something that comes from the next order, it will automatically be zero.
And what about the alpha beta? Yeah. First one is both is alpha, but second one is alpha and beta.
I want it to be zero.
So
Let's check the proof for the future. Yes.
the wave function beta is only linear combinations of beta, right?
Mm-hmm.
So therefore, if it's any linear combination of beta conjugated with alpha, it's always zero because it's first order
Mhm.
wave function. First order is always zero.
So what do we have after these simplifications? Probably this part will be for later. If someone needs to go, but it will be recorded and distributed. If you do something not boring and colorful. So let's just play another round of calligraphy and repeat this expression with all the E simplifications. The perturbation to in matrix element in basis of unperturbed. And since we are already very tired of calligraphy, we should make a shorthand notation, maybe H prime alpha alpha. It will save us 3 symbols instead of 10. Next, C sub beta. How can we call this one?
H prime beta alpha beta.
H
Prime
prime.
alpha beta.
Yes, it's better. Now,
But wouldn't all the other terms be zero?
no. This, we are going to cancel something and
Oh, that's on the same. That's on.
all activity that we are doing is to find this E1.
The next two terms are the ones that alpha is 2 on the right side. Right?
Let's think. So what you are telling that the one with tilde
Same as-
is the same as the one with tilde here.
Even the energies.
Because the energies are
Zero.
zeros order. So let's put 0 here. And if you do dashes on the top, zeros first, alpha, beta, E sub alpha. Zeros first, alpha, beta, E sub alpha. So it doesn't matter are they 0 or not, but they are cancelled. Here and there. Good eye. Then we have, so it was 4 equals 4, 4 terms on the left, 4 on the right. Now we are, it will be like 2 equals 1. So on the right, we will have first order correction to the energy, C sub alpha. That's it. What will happen if we go one step back and multiply everything by bra from the left of the degenerate state with index beta? I'm just guessing it because of the symmetry, but if any of us have doubts, we can go and play this calligraphy once again. Aren't you happy to see these two equations? You should. Let me make a shot, release the space, and then analyze it, because we are like half inch from the answer. So I'm erasing everything except these two encircled equations. And how do we interpret them? What is shown in these two equations? What is known and what is unknown?
So we know the coefficients.
Well, no, we do not know the coefficients.
Oh, good.
Because it is the degenerate, we do not know how they are prepared. And we do not know the energy because it is a correction to the energy. But we do know the solution in absence of perturbation. So we know the zeroth order wave functions, and therefore we know for sure this perturbation matrix elements, right? How can we rewrite this equation? Does it remind something? I don't know how to make this pedagogical step, but well, I looked in a textbook. Maybe I will spend more time to recognize it, but we can consider all known parts, H of H beta alpha, bless you, H beta beta.
Oh, it looks like matrix.
Yes, perfect. Then we are multiplying first of them by C alpha, second by C beta. Can we consider it as row by column? We need to diagonalize the matrix and find eigenvalues and eigenvectors. And here it should be a prime because of the perturbation. So it could be assumed that most of the states, most of the orbitals, most of the levels are non-degenerate, but there is a small fragment that are degenerate. And then we forget about everything else, take the small fragment, and then for it, we still need to do matrix diagonalization. The benefit is that we can forget for time for other states. But okay, how would we deal with this? How do we diagonalize matrices? We're doing H prime of alpha minus E first correction. H prime beta, H prime beta alpha, H prime beta beta minus E. multiplying by this vectors equals 0, which means that determinant of this matrix should be 0, right? What does it mean, determinant equals to 0? Well, for matrix of 5 by 5 that Levi is going to present in 5 days, it is something more complicated. But for my simple case, it is a little easier. So we are doing H prime first order correction. So what is unknown, what we are going to find? We need to find the energy, right? So it's square second order polynomial equation for energy. So what do we do in our middle school and high school when we see a question like this? We are combining terms, second order, first order, and zeros order. And immediately write the solution. So coefficient in front of first order A, coefficient in front of the first order B, coefficient in front of zeroth order C. So the energy will have two branches, plus and minus. Sam, would you like to remind us how to solve second order polynomial equations? You can write first in general terms, in terms of A, B, and C, and then I like it. So let's check. You'll probably help to go a little further, but let's ask help of the club and check if the equation is correct.
A?
A here?
No.
No.
B minus B
It's B.
minus B.
It's minus B.
Fine, minus B, whatever.
It's
Okay.
not whatever.
Hey, fine, minus B.
Just go and
Okay. If you're tired, you can ask someone else, or you can start plugging in the parts.
I'll pass it up to Levi. He's really pretty good.
Okay, thank you so much. Good. Thank you much. So this is already a good answer. So it will be first order correction to the energy. So our energy of degenerate states, we had two states, each of which was having energy of in zeros order. But in the corrected way, it will be E alpha of the zeros order plus first order correction, which is introduced by Levi. And this is nice and correct. We can use zeros order wave function to find matrix elements, but it's a little too long and too general. Let's look on the simplified case when the perturbation does not introduce transitions between these states. When the perturbation only affects their energies, when the perturbation has only diagonal character. Who was not visiting the blackboard? So, would you please rewrite this expression in case if diagonal matrix elements are equal 0? Or maybe use space right here because it could take a while. So H alpha beta and H beta alpha equals 0. Where do you go to imaginary? I think it is specific.
It's not. It's not immediate. It's not.
Are you going to? What are two first terms? Or you?
What because of diagonal elements are
Yes.
zero, right?
Diagonal elements are not zero, and off diagonal.
All diagonal
Yes.
elements are non-zero.
Correct.
Oh, okay. So this will be zero
Yes.
only. All right.
Mm-hmm.
Okay. And this is
Please write a minus here because it is either plus or minus. Right.
Is this just minus b?
It's a plus because that was a
it's
minus.
already negative.
It's negative.
Yeah.
only
Is
there.
it already? It's already negative, so it's positive. Okay. So it is minus b. Okay.
Mhm.
So. So this is H alpha alpha. So H alpha alpha prime H beta beta prime
and plus between them. It's summation, not product.
Oh.
Okay.
H alpha
Okay.
alpha minus H beta beta whole square. We
Plus
consider
minus
minus 4
H
Alpha,
alpha
alpha.
alpha
alpha b.
prime plus
We simplify, we will get minus.
the cross.
Something can cancel.
Okay. So this
But
is
don't hesitate to write more than one line.
plus, so there is
He's
a
a
plus,
physicist. He wants
plus
to do
2, so
everything.
there is a minus 2. Yeah, so this is H alpha prime minus H beta prime. That's it.
To be H alpha alpha.
Should we divide it by 2?
Yeah.
Yeah.
So can you write explicitly E prime plus E prime minus?
Oh, okay. E prime plus equals H alpha prime plus H beta prime plus
That will cancel.
H alpha prime minus H beta prime
Divide by 2
divided by 2
equals. Next one is fine.
It's just H alpha.
Okay. And what will be for E prime minus?
Minus prime. Okay, so now H alpha will cancel. Negative. Positive. H beta. H beta minus H alpha plus H beta. So you have 2H beta divided by 2, so this is H beta.
Yeah, very good. Yeah, thank you. So this is very trivial. We could have guessed it and not spending time in front of the board. But it means that we can find the matrix elements for diagonal element in basis of unperturbed waveforms, which are known. And then just add them to the unperturbed value of energy. E0 plus H alpha alpha, E0 alpha plus H beta beta. So the whole effort converts into accurate, careful calculation of matrix elements for the 2x2 case. If it is bigger matrices, it is a little effort to diagonalize it, but sometimes with symmetry, it also can be done simply. And it turns out that if one changes the parameter of interaction, which can be like strength of ligand field or proximity of ligand or whatever, the signs of these corrections are different. So they either change with opposite signs, or even if the signs are the same, they change with different pace, different rate. So if this is perturbation, and this is energy of the state, then energy of level splits, and the right word here is degeneracy is lifted or removed. So interaction removes degeneracy, lifts the degeneracy. Plus minus. One of the examples that we hope to hear next Tuesday will be how the degeneracy is lifted among d orbitals. When we go from isolated hydrogen-like atom to atom with explicitly available d orbitals in presence of another atoms and molecules called ligands. So their electrostatic field may induce splitting of the levels. And this is a simple application of perturbation theory from point of quantum theory. And it is extremely widely exploited common knowledge in chemistry, the crystal field splitting. I think we are over the time today. Thank you much for being patient and for your enthusiastic contribution to these derivations. Meeting is over. Thanks for coming. We are going off records. I'll stay here for questions.